Okay, so in this video we're going to do a few more example problems with decay equations, and then briefly talk about ionizing radiation, and then in the next video we'll talk about half-life and radioactive decay. So take a look at this example problem here. Now we have a radioactive decay equation with some missing blanks in it. Something you should know is that on the IB exam, you're not given a periodic table in IB physics, which means that typically when you're given a question about a decay equation, they write it in such a way where you don't actually need a periodic table to answer the question. Okay, so for example, if you look at this equation, we have two blanks here. We have potassium 42, that is our parent nucleus on the right, that is obviously what's radioactive in this case, and the daughter nucleus is shown, on the left, and the daughter nucleus, calcium 42, is shown on the right. In other words, potassium 42 is radioactive, and it undergoes radioactive decay because it wants to become more stable. We've talked about that before. And it ends up as calcium 42, which is at least more stable than potassium 42. Okay, and in the process it emits some particles. Now, the first question says, state the type of decay shown. Now, we can do that very easily as long as we remember that in any nuclear reaction equation, the atomic numbers and the mass numbers have to be the same on both sides of the equation, if you think of this arrow as an equal sign. So if you take a look, we have a mass number of 42 on the left side and a mass number of 42 on the right side. Those two are balanced, and so these two blanks here don't have to have any numbers in order for those two things to be balanced. However, if you look at the atomic numbers on the bottom left, we have 20 on the right, 19 on the left, and so there has to be something to be added here on the right side so that something plus 20 equals 19. And so hopefully that's obviously going to be -1. Okay, and the only thing that is 0, -1 is an electron, aka a beta particle, in this case a beta minus particle. So the type of decay is going to be beta minus. Okay, now the reason there's another blank is because remember, anytime you have beta minus decay, you automatically have an anti-neutrino. Okay, which we're going to do like this. This is a Greek letter nu. It looks kind of like a V, but it's a nu, N-U. You can look it up if you want, with a line over it to indicate that it's an antiparticle. Okay, so this would be the completed radioactive decay equation for potassium 42 undergoing radioactive decay. It's beta minus decay and turning into calcium 42. Okay, so pause there if you need to take a look at that. We're just going to do a few more examples. Okay, so take a look at this example. This is example 1.5. This is actually from a previous IB exam. Okay, and it says, which of the following correctly identifies the three particles emitted in the decay of the nucleus? Let's see if I can make that bigger. Calcium 45 into a nucleus of, I think SC is strontium, I'm not sure, or scandium. Luckily, you don't need to know what the elements are to answer the question. It's whatever 45, and we can see the atomic number of both. So this is an IB question, and you can see it's asked in a way where we don't actually need a periodic table to answer this question. Okay, so what three particles are emitted in the decay of calcium 45? So if I start with calcium 45, okay, I'm given that information, and it says into a nucleus of this. Okay, so I'm just going to write what the product is going to be. Okay, that is the daughter nucleus. So I can easily do basic math and figure out, okay, this is 45, this is 45, the mass numbers are the same, but there has to be a -1 down here to make this balanced. Okay, so this would be 0, -1, E. Okay, and oh, hey, it's beta minus decay. Okay, that means we have to have an anti-electron neutrino. Okay, so what two particles have to be emitted? Well, obviously, there has to be an electron, a beta minus particle, and a anti-neutrino. Okay, so I want to choose the answer that has those two particles. Now, if you're looking, notice that this top one does not work because there's not the antineutrino. This one has 3 particles. We only identified 2, and you might ask, what is that particle in the middle that kind of looks like a Y? Well, that is a gamma particle. Okay, wow, that was a bad gamma. Pretend that was a good gamma. And I do want to remind you that gamma particles are emitted in most types of radioactive decay as kind of like an extra product. Okay, and so B is actually going to be the correct answer because it's the only one that works. C does not have the beta minus particle we need, and the problem with D is it also has an alpha particle. Now, if there was an alpha particle over here as another product, then the numbers would not match up, right? Because remember, an alpha particle is 4, 2. It has a mass number of 4 and an atomic number of 2, and so the numbers would not match. Okay, so the answer has to be B, because even if we did have a gamma over here, remember gamma is also 0, 0, and so it wouldn't change any of our answers. Okay, so that one is fine. Okay, so this is an example of what an IB question might look like for this particular topic. Okay, so pause it there if you need to take a look at that. Okay, I'm going to erase this, and we're going to take a look at one more IB question. Okay, example 2. This is also from an IB exam. This is actually just a couple of years ago, so this is a more recent question. It says nucleus P decays by a sequence of emissions to form nucleus Q. 1 alpha particle and 2 beta minus particles are emitted during the sequence. Which statement is correct? Now, if you don't know what that means, a sequence of emissions, remember, we've looked at this picture before, that when something is radioactive and it undergoes radioactive decay, it wants to become more stable. Now, the daughter nuclei it turns into may not be stable, and so it might undergo radioactive decay again in a series of emissions. So, for example, we looked at this picture before where uranium-238 decays into thorium-234, which is also radioactive, which, decays again and again and again and again in this series of emissions. And so that's what's happening here. Now, the easiest way to do this question is basically to start with nucleus P, and I would say this is a medium difficulty question. As long as you understand the concepts of what's happening, you can easily figure this out. But this is a concept question. So it says nucleus P. That's what we start with. Okay, nucleus P, let's say it has an atomic number of an atomic number of Z and a mass number of A, and it decays by a sequence of emissions to form nucleus Q. So nucleus Q is going to be a product. Now, I do want to point out that what I'm about to write as this reaction equation is not completely correct, because nucleus P does not turn into nucleus Q directly. It goes through a sequence of emissions. It goes, through some intermediate stages. But we're going to ignore that just for the sake of this problem, just to make it easier to solve. Okay, so nucleus P doesn't actually turn into nucleus Q, but we're pretending it does just for this problem. 1 alpha particle and 2 beta minus particles are emitted during the sequence. Okay, so that means as products, I also have 1 alpha particle, which is 4, 2 alpha, plus 2 beta minus particles. Okay, so I'm going to have 2 out in front electrons. Now, I guess I should also have 2 antineutrinos, but that doesn't really matter because it doesn't change any of the numbers I need. Now, which statement is correct? Well, I know because of the way the math works in these nuclear reaction equations, that the mass numbers have to be the same on both sides, and the atomic numbers also have to be the same on both sides. Okay, so let's look at the mass number for Q. Okay, so I have on this side, I basically have A on the left, and on the right I have something plus 4 plus 2 times 0, which is 0, plus 2 times 0, which is 0. And so the mass number of Q basically has to be a number that when I add 4 to it, I get A. Okay, that means the mass number of Q has to be A minus 4. Because if you take A minus 4 and you add 4 to it, you get A. That's how that works. Now, if I also look at the atomic numbers, I know they have to be the same on both sides. On the left side, I have Z. On the right side, I have to have a number down here so that this number plus 2 plus Now, I have 2 electrons, and so 2 times -1 is -2. I have 2 antineutrinos, 2 times 0 is 0, and so my atomic number for Q has to be such that when I add 2 plus, let's see, -2, I get Z. Well, 2 plus -2 is 0. So basically the atomic number of Q has to be such that when I add 0 to it, I get Z. I wonder what that could be. Clearly has to be Z, because Z plus 0 is also Z. By the way, I know my handwriting is bad. Please don't confuse my Z's, which have a line through them, and this 2 down here, which is just a 2. Okay, so look at this for a second. Convince yourself that this works. Z plus 2 plus -2 is the same as Z. Now, I have this equation. Now, how does that help me answer this question? Well, first of all, if they have the same atomic number, then by definition they are the same element. Okay, that's what defines an element, is the number of protons in that nucleus. If they have the same number of protons, they have to be the same element by definition. Okay, so what's the difference between P and Q? They have different mass numbers. That means they have different numbers of neutrons. If they're the same element with different numbers of neutrons, then that means P and Q must be isotopes of each other. So the answer is B. Okay, and the other ones don't work. A doesn't work because, well, it just doesn't. They don't have the same number of neutrons. They have the same number of protons, but they have different mass numbers, which means they have the different number of neutrons. C doesn't work. P doesn't have a greater charge because they have the same atomic number. They have the same number of protons, and there's nothing in the problem to suggest anything about the charge. And D also doesn't work because they have the same atomic number, so they have the same number of protons. Okay, so that question is kind of medium difficulty, but if you understand the concepts involved here, it's definitely a doable problem. Okay, so those are just some basic examples from previous IB exams over radioactive decay. Now, one more thing I want to talk about in this video is ionizing radiation. Okay, so I'm going to erase this. And let's move on. Okay, this graphic right here is basically just summarizing the 3 types of decay we've talked about, although it does not include beta plus decay and the neutrino or antineutrino that comes with it. So the last thing we're going to talk about is background radiation and ionizing radiation. Okay, so you do need to be aware that there's a lot of natural radiation in the world. Now, there's artificial radiation because we can produce radioactive substances. We'll talk about that later. But there is actually a lot of natural radiation in the world. There's radiation coming from space. There's radiation coming from the ground. Radon can seep up from the ground. Stuff can get, into the air. A lot of the food you eat, bananas, for example, we talked about have potassium, and some isotopes of potassium are radioactive. So there is natural radiation all around us. Okay, so you do need to be aware of that. Now, as far as the biological effects of radiation, we're not going to go into a lot of details about this, but I do have some videos I want you to watch that I'm going to link in down below and in the video. So, we've talked about this before, but alpha, beta, and gamma particles are capable of ionization. And we also talked about what ionization is. That ionization is basically just the ability to remove an electron from an atom, thus creating an ion. Now, these are not the only things that can cause ionization, of course, because any type of particle or energy capable of removing an electron from an atom can cause ionization. But since we're talking about radioactive decay, this would be a good time to talk about ionization. Okay, so make sure you add this to your notes and you know what ionization is. The biological effects of ionization I'm not going to get into because that's a little outside my field of expertise. But like I said, I am going to link these videos down below. I can tell you that ionization can have serious medical implications for humans because cells and DNA are made of atoms, and if those atoms become ionized or otherwise damaged by radiation, they can stop functioning correctly. Okay, which can result in medical complications, mutations, cancer, death, stuff like that. Okay, and there's no way to completely avoid radioactive materials because, again, there's natural radiation all around us. Okay, so watch these two videos I'm going to link down below, and they're going to talk about, ionizing radiation and some of the biological effects of ionizing radiation. And then let me know if you have any questions, or you can do your own research, because this is something that kind of goes outside of IB physics, but is really interesting to know about the dangers of ionizing radiation. And again, there's different types of ionizing radiation. We're only talking about alpha, beta, and gamma particles causing ionization just because this unit we're on just right now has to do with radioactive decay. Okay, so the last thing in this video, once you watch these videos, the last thing in this video I want you to add to your notes is this definition right here. You'll notice that an element undergoing certain types of radioactive decay will change into a different element. The changing of one element to another is known as transmutation. Okay, that is a definition. That's why it's in bold. You should definitely add that to your notes. Typically, when you have radioactive decay, you have some type of transmutation, one element turning into another element. And we saw that before in all of the examples we've done. Here we can see a chain of different transmutations, starting with uranium-238 and then ending up all the way down here at lead-206. Okay, so transmutation is the technical term for one element changing into another. Okay, so make sure you add that to your notes. In the next video, we'll talk more about the law of radioactivity, radioactive decay, and half-life. And then after that, we'll move on to the next part of this unit. Okay, so as always, please let me know if you have any questions, and I will see you in the next video.